Let's start with something simple. Here's a square grid. 10 tiles across, 10 tiles down. So that's 100 tiles total. 10 times 10. Now, some of these tiles are special. The ones around the outside edge, the border, those are going to be a different color. Watch. There they are, the border tiles. And here's the question we're going to spend the next 10 minutes on. How many of those blue tiles are there? Now, before we start counting, let's be clear about what we're counting. We're not finding the perimeter. Perimeter is a measurement. It's the distance around the outside, like if you walked along the edge. We're doing something different. We're counting tiles. Each one of these blue squares is a tile, a separate piece. We want to know how many individual tiles make up that border. It's a small but important difference. We're counting things, not measuring distance. So, how many are there? The obvious approach, just count them. 1, 2, 3, 4, 5, 6. You could do that. But there are a lot of border tiles on a 10 by 10 grid. And what if the grid were bigger? What if it were 20 across, or 50? Counting one by one would take forever. So here's the challenge. Can you find a way to figure out how many border tiles there are, without counting them one by one? The trick is to look for groups. Find chunks of tiles that are easy to count, and then add them up. And I'm going to show you 3 different ways to do exactly that. 3 different ways to see the same grid. Ready? All right, method 1. Let's start with the parts that are easy to see. Look at the top row. How many tiles in the top row? Well, the grid is 10 across, so that's 10 tiles. Now look at the bottom row. Same thing, 10 tiles. So we've got 20 tiles so far. Now what about the sides? Here's where you have to be careful. Look at the left side. You might want to say the left side has 10 tiles too. But look at the corners. Those corner tiles, the one at the top left and the one at the bottom left, we already counted them. They were part of the top row and the bottom row. If we counted them again, we'd be counting them twice. And you can't put 2 tiles on one spot. So each side doesn't have 10 new tiles. It has 10 minus the 2 corners we already counted. That's 8. So let's add it all up. Top row, 10. Bottom row, 10. Left side, 8. Right side, 8. 10 plus 10 is 20. 8 plus 8 is 16. 20 plus 16, 36 border tiles. 36. That's our answer for method 1. Now let me show you something completely different. Method 2 takes a totally different approach. Instead of being careful about the corners from the start, what if we just ignore the problem at first and fix it later? Watch. The top side has 10 tiles. The right side, 10 tiles. Bottom, 10. Left, 10. 4 sides, 10 each. 10 plus 10 plus 10 plus 10, that's 40. But wait, 40? That seems like too many. And it is too many. Here's why. Look at the top left corner tile. When we counted the top row, we counted that tile. And when we counted the left side, we counted it again. The same tile counted twice. Because you can't put 2 tiles on one spot. But we counted like we could. And that happened at all 4 corners. Top left, top right, bottom left. 4 corners, each counted twice. So we've got 4 extra tiles in our count. The fix is simple. Subtract them. 40 minus 4, 36. 36 again. The same answer as method 1, even though we thought about it completely differently. Think about that for a second. 2 totally different strategies. One was careful from the start, avoided the corners. The other was messy on purpose, counted everything and cleaned up after. And they both got 36. We've seen 2 ways, and they both came down to the same problem. The corners. In method 1, we avoided counting them twice. In method 2, we counted them twice and subtracted. So here's a question for you. Is there a way to group the border tiles so that every side gets exactly the same number, and the corners aren't a problem at all? Take a look. Here's the trick. What if each side claims just one of its corners? Not both, just one. Watch how that changes everything. The top side takes the top left corner. That gives the top group 9 tiles, not 10. The right side takes the top right corner. 9 tiles. Bottom takes the bottom right. 9. Left takes the bottom left. 9. 4 groups. Every group has exactly 9 tiles. No overlap. No corners to worry about. Every single border tile belongs to exactly one group. 4 times 9, 36. Same answer, third time. Let's put all three together. 3 completely different ways of looking at the exact same grid. 3 different expressions. They don't look anything alike, but they all equal 36. Every single time. When 2 expressions always give the same value, we call them equivalent expressions. They look different on paper, but they mean the same thing. And the reason they're equivalent isn't just luck. It's because each one describes a real way of grouping those tiles. The math matches the thinking. And by the way, if you found a way that's different from all 3 of these, that's not wrong. That's another equivalent expression. But here's the real question. Does this only work for a 10 by 10 grid? Let's try a smaller one. Here's an 8 by 8. Using method 3. Each side takes 1 corner. Each side has 7 tiles, 4 groups of 7, 28 border tiles. And if you check with method 1, 8 plus 8 plus 6 plus 6, that's also 28. It works. These strategies don't just work for one grid. They work for any square grid. The numbers change, but the thinking stays the same. And that's the real power here. Once you learn to see the groups, you can count the border tiles on any size square. Before you go, 3 things to take with you. First, use color to make your thinking visible. When you group tiles by color, anyone can see your strategy just by looking. Second, look for equal groups. Count how many groups and how many in each group. Third, different strategies give different looking expressions, but the same answer. That's equivalent expressions. And the more ways you can see a pattern, the more powerful your thinking becomes. Next time, we're going to look at a pattern that grows, and you'll use these same skills to figure out what changes and what stays the same.